All right, in this lecture we are going to talk about duality. And duality is a word that shows up a lot in this subject, and we've already used it once to connect V with its dual space V star. And that is a form of duality, but we're going to talk about something a lot more specific than that. You may remember that when we created the vector space V, the vector space V star, its dual space, appears automatically because V star was the map, if you remember how we did this back in the day, the map from V, which was a four-dimensional vector space, or a vector space of some number of dimensions, and it was a map from that vector space into its field, its constructive field, which is usually the real numbers, although it could be the complex numbers or any other field, such as the quaternions or the octonions, which I guess is O. And I think octonions are usually given by H. Or is that the quaternions that are given by H? I can't remember. But there's these four fields, but it could be any field. Doesn't have to be just those four. But we always dealt with the real number field. And that created this notion of the dual space. But you'll remember that the vector space, a map from the vector space into the dual space, there was no single mapping that went from the vector space to the dual space. Remember, every element of the dual space represented some map between V and R, right? And all those maps together was, all those maps collectively was the dual space. But now, what if we were to consider mappings from the vector space to its own dual space? We don't have any single mapping that jumps out at us. No natural mapping, I guess, is what we would say. Or canonical mapping, right? There's no canonical mapping between the vector space and the dual space. And that's only if the vector space is not an inner product space. If there is an inner product, then there is a canonical mapping. And that canonical mapping is driven by the existence of this inner product. But assuming we do not have that inner product, there was no canonical mapping. None of that existed. However, there's a general notation that expresses, again, the same principle as we did with the dual space. What about the set of all possible mappings between V and V star? And that's often written this way, HOM V star, which is a generalization of this notation, HOM V W. That is the set of all maps, all possible maps between the vector space V and the vector space W. And V and W do not have to have the same dimension. But if we stick in for W the dual space of V, we get this, the set of all mappings between V and V star. And that's the best we can do. And of course, this HOM mapping between V and V star, that automatically exists just like the dual space automatically exists because we have these two sets. So I guess when you think of it this way, we create V and it comes with its field. And when the creation of V automatically creates the existence of V star, right, which is also a real vector space. And once we create the existence of V star, which automatically happens canonically, it has to be there, well then all of a sudden this thing has to be there, right? This mapping has to be there. And that's HOM V and V star, right? So now that has to be there. And you can almost imagine chains of this going on and on forever, right? And that's true. That's going to happen, right? You're going to have, there's other mappings between these sets that automatically pop into existence. The point is that this is still a set of all possible mappings between V and V star. It doesn't pick any one of them out. So, again, once we introduce the inner product, right, now all of a sudden the dual space still exists, but now there is a specific mapping between V and V star that's really, really good, right? It's forced upon us, and it's actually an isomorphism, right? It's an isomorphism between V and V star, and that one mapping is what allows us to basically take vectors in V and correlate them with specific vectors in V star in a canonical way. Now all of a sudden it is canonical. But we've made it canonical because we've introduced an inner product. So this vector space is now a deeper, more complex structure. We've introduced our own favorite inner product, and once that was happening, now we have a single mapping that stands out. This still exists, but there's one guy in here that is special, and that special one ultimately is mimicked by the metric tensor. And the mapping would go something like this. It would go for every v, so if I took a v as an element of the vector space, if I create this map, right, I'll put the little v there to show that this is the inner product in the vector space v. This thing here, right, it's waiting for a dual vector, right, so some dual vector goes in there, and out will pop a real number. So this object here that I've just written down, this thing right here, that is a map from V from V to well, I guess the way I wrote it here, that's a map from V star to R. So this would be a map from V star to R. And oops, no, wait, let me say that correctly. I don't want to cause it's easy to get mixed up here. This thing here that I put a box around, that actually is an element of V star. And it's the element of V star that correlates to V. And this thing here is how we do the mapping. So we take V and we map it to this object. That object is an element of V star, right? And in fact, it's the exact element of V star that's favored by this canonical mapping because it's driven by the existence of this inner product. Okay, so that was, so that's a form of duality, right? First of all, the usage of the word duality in the sense of a dual space, we've already explained what that is. That's this massive set of all possible maps. That's the dual space. And in some sense, that is a duality on the entire set V. But that's not what we're interested in. This guy here is a duality because it is the duality that we're talking about. When we say looking for vectors that are dual to each other, we're looking for these favored maps, these maps that exist automatically and aren't part of these massive sets of maps. We're looking for these favored single maps between one vector space and another vector space. And in this case, the one vector space is our sort of anchor vector space V, and the other vector space is its dual. So there is a duality between V and V star, but only when V is an inner product space, and that duality is given by this expression. So that's our first concept of duality that exists in our work. It's the duality between vectors in the inner product space V and V star. And it goes both ways, by the way, right? The duality goes both ways, right? Because if it's going this way, then the guy here is V star V, and if it goes this way, then the duality is V like that. And this here is a member of that space, and this here is a member of that space. And that's a one-to-one correspondence, and it's an isomorphism. And for every vector in V, there's a dual vector in V star triggered by this relationship. So that's our first sense of duality. And it comes down to, in a practical terms, any member of V, right, that's a member of V, can be associated with a member of V star. And that is through this raising and lowering of indices. And in the classical notation, where we skip these basis vectors, we basically, the duality is driven by the metric tensor. A mu nu is G mu nu A nu, right? That you raise and lower indices through the metric tensor. And the metric tensor is the tensor equivalent of this. It's the 0, 2 tensor that actually, well, in this case, it's the 2, 0 tensor the way I've drawn it here. I could have gone this way, A mu equals G mu nu A nu. That would be the 0, 2 tensor that embodies this inner product, and this is the 2, 0 tensor that embodies the same inner product, but these both reflect a map from, in the classical language, a covariant to a contravariant tensor. Of course, yeah, I can't help but remind you, the covariant tensor, right, is actually just the covariant component of a basis vector that is actually contravariant, and the contravariant tensor is actually the contravariant component of a covariant basis vector, right? Just keep that in mind. I really, the more I say that, this is getting late in the game to keep reminding you of this, but it's still an important point. So anyway, that's our first concept of duality. Now let's go to more interesting dualities. All right, so let's draw the universe tree of the sets that we can play with. And this will now draw on all the things we've learned about forms. I guess we could start with the 0th exterior power V of a set V. You know, I'm going to, just for this lecture, I'm going to get rid of this. We're always going to assume that the pth exterior power is operating on a set V, and if the p is in the in the superscript position, we're dealing with forms that are constructed out of the dual space, right? And where there's going to be p of these. And if it's in the lower position, we're always going to assume that that is, that is, this is weird. It's like upside down wedge, wedge, upside down wedge, wedge, wedge. My V's and my wedges are just so similar, I guess. And then there's p of those, right? And the fact is we're always going to assume V here. There was one lecture where I kind of screwed this up, and I did P star V star like that in order to mean this. But that's redundant, right? If I put something in here with a dual space, then the fact that this is up or down becomes irrelevant in a sense, right? So in order to make it not redundant, this really should be PV, where I understand because it's in the upper position, I'm dealing with the dual of this sort of set argument. On the other hand, I just read an article not too long ago that did it this way, and because redundancy isn't always that bad, but this is literally confusing if you don't do it right. Because in my world, the way I want this written, this thing would actually mean, this thing here would actually mean V star star wedge, V star star wedge, which would be V wedge, V, etc., like that, right? So that's not what I want. So I'm sticking with this notation, but for now, I'm going to even simplify it more, and I'm just going to write like that, without any argument here. Okay, so with that in mind, let's do this again. So this thing now, the 0th exterior power, that is very, very similar, and in fact, it's really the same as this, right? Because when you're dealing with the 0th exterior power, you don't have any terms of the vector space or the dual space. But we do want to kind of make a distinction between the two, even though they really, really are the same space. They're the space of all C infinity functions on the manifold, right, that we're dealing with, or in space-time, or I guess we don't, I'm not counting on the fact that you guys have covered the manifold lectures that I did, so I kind of want to avoid the word too much, but let's just say on the space-time. So I'll put it on the space-time S, where I basically mean a function, a C infinity function of the coordinates. So that's the two 0th exterior powers, and they both have dimension 1, right? Now the question is what dimensionality is the underlying vector space V we're dealing with? And I guess let's play with Well, let's use 4 as a specific example. I could choose to use 4 as a specific example, or I could try to use n and just do it in full generality. Let's stick with 4 for right now. So now I have a chain of exterior spaces. The first exterior power, the second exterior power, the third exterior power, and the fourth exterior power. And there's no others, right? If we deal with n equals 4, like that. And then over here, I guess we have this first exterior power, this second exterior power, the third exterior power, and the fourth exterior power, right? And these, of course, are going to be P vectors, and these are going to be sets of P forms. So now we know that the dimensionality of these guys is the same. The dimensionality of this is 4. The dimensionality of that is 4. The dimensionality of this is, let's see, dimensionality of this is 4. Dimensionality of this is 6. The dimensionality of this is 4. And the dimensionality of this is 1. And the same is true, and this is meant to be true across both sides, right? So these all have the same dimensionality. So we can always establish, and we're also assuming, of course, that V is an inner product space. So I'll go with V and then V like that. It's a real inner product space, so it's on the real numbers, and its dimensionality is 4, right? So that's what this is V, right? V is this collection of things. A set V of all the vectors, an inner product on V, it's a real numbers for the vector space, and the property that it has the dimensionality for. So with that in mind, we can look at this thing and we can say, well, what things have the same dimensionality? And can this inner product, is that inner product enough to establish a relationship between the two? Well, this has the same dimensionality as this, right? That has the same dimensionality as that. So that is a relationship that we can probably tease out, and we already have. And that duality, the one-to-one relationship, the natural canonical one-to-one map between the first exterior power and the third exterior power is called Hodge duality. And it's by far the most important one. And the same thing exists here. Hodge duality. Now what's interesting about Hodge duality, well, first of all, those aren't the only two that have the same dimensionality. It turns out that this guy here and this guy here have the same dimensionality. So there's got to be a Hodge duality relationship here also, right? All of the ones in red are Hodge duality. And does that take care of everything? Well, it does, except for this guy, right? This guy doesn't have anybody else that has the same duality relationship. So what about them? Well, it turns out that these spaces are self-dual. So there is a Hodge duality here, but it looks like this, right? There's a Hodge duality like so for this space. So every vector in the universe, or in the pantheon, I don't want to say the universe. Universe is to cosmology. So let's say pantheon. In the pantheon of exterior powers, every exterior power has a Hodge duality as long as we're dealing with an inner product space, right? That's the key. You got to have an inner product. And this concept's really important because in general relativity, the inner product is everything. The inner product is essentially what general relativity, in the view that I like to talk about it, it's the most important thing because it is the metric tensor, and the metric tensor is the answer to almost every really, really, really interesting fundamental question in general relativity. So demanding an inner product is not exceptional. It's what makes it powerful, right? Right now we're talking about one vector space V, but of course ultimately we're talking about vector fields over space-time, and then we have vector fields where each vector space at every point in space-time has its own inner product, and the totality of all those inner products is captured by the metric tensor g mu nu, which is a function on space-time. And that thing is what ultimately it creates the geometry of our space-time, which is influenced by the mass distribution, the energy distribution sitting in space-time, and that's what tells us how things move. That is the answer to the physics questions that we're seeking. So with that in mind, the existence of this inner product, which is what drives the existence of these Hodge's dualities, not a surprise. So we'll talk about Hodge duality first. But while we're on this chart, you might as well see, well, what other things have an obvious dimensional connection? Well, there's the connection between this guy and this guy, right? This guy and this guy, right? There's this connection here. There's that connection there. When I say connection, I'm saying what spaces have the same dimensionality. Because in order to have a one-to-one correspondence and an isomorphism, the vectors between vector spaces, a natural mapping, you have to have the same number of dimensions, right? So this has dimension 4 and that has dimension 4. This has dimension 4 and that has dimension 4. Now this connection is actually pretty simple, right? This connection is just driven by this very sort of standard idea that anything in here can be written as A, alpha, beta, gamma, delta, dx alpha wedge, dx beta wedge, dx gamma wedge, dx delta. Usually there's a 1 over p factorial here, and these coefficients are understood to be totally antisymmetric, and they would be the same coefficients as you would see in, they'd be the same coefficients that you would see, damn it, I keep drawing that leg. The same coefficients, alpha, beta, gamma, delta, dx alpha, O times dx beta, O times dx gamma, O times dx delta. If I understood these to be totally antisymmetric, then this is a totally antisymmetric tensor. If I convert it into the non-strict basis, then these components are identical to those components, but then I add this 1 over p factorial for compressing, because I end up compressing the basis. The point being that I can raise and lower these guys all I want using the metric tensor, right? And if I raise or lower these guys using the metric tensor, then essentially that will raise and lower this guys as well, which will convert anything in here into something into there. And that is just a restatement of this duality right here that we talked about earlier, right? This duality here that we described in the beginning is trivially brought over in a relatively uninteresting way between these spaces here. All right, let me do a little bit of so these spaces here are connected by the standard dualities, the standard duality of the metric. There's no real word for that, actually. I'll call it the metric duality. How about that? The metric duality. We won't discuss it anymore because I just did, right? This is the metric duality, essentially. You take these guys, you could say, take an element of this, write it in this form, right? Raise all the indices, and convert it back into this form, and you essentially now have created the metric duality. It's pretty easy to do. All right. Let me clean that up a little bit. Hold on. Okay, there, cleaned it back up. So we have this thing called the metric duality also. I'll write it again down here. All right, so now what about other dual relationships? Well, I mean, it's pretty obvious, right? You've got a four-dimensional object here, right? And shoot, I'm missing one of the Hodge dualities, right? So this is a Hodge duality too, and I guess this is a Hodge duality also. Do I need to write every one of them? Why not? Okay, so now we've got all the Hodge dualities, right? This one, we've got this one, this one, this one, this one, this one, and that one. Now notice this self-duality doesn't exist if the total dimensionality of V is not even. If it's even, you've got this sort of middle guy. Because remember, you start at 0. So you really have an odd, you end up having an odd number of these exterior powers. You have n, in this case 4, plus 1. So when you have an odd number, you always have this guy sitting straight in the middle, and you have this self-dual exterior power. So you don't always have that. If this was if n was odd, the two inside ones would just would pair up, and there wouldn't be any self-dual space. Okay, metric duality. Now what about this? This one has dimension 4, and this one has dimension 4, right? So there is a duality there, right? So I'll make that one green. Right? There's that duality, right? And likewise, of course, there's this potential duality. When I say duality, I've got to kind of prove the duality exists. I'm just saying these guys have the same dimension, right? Dimension 4, dimension 4. Likewise, this has dimension 4 and dimension 4, and this has dimension 4 and dimension 4, like that. And then this guy here, dimension 6 to dimension 6, can go like that too. Interestingly enough, it's just like the Hodge dual, or it's just like the metric dual. So there's those possibilities. Why am I repeating this one? Right? We've already kind of shown that the metric duality connects them. Well, I'm implying that if there's a connection here, it's different than, it's not, this one certainly isn't the same as the metric duality, right? So there's possibly this connection too, using whatever technique I go from here to here, and whatever technique I make connect these two spaces, I can use the same technique to connect these two spaces. Now we have yet to show that if I do that, do I come up with something different than the regular metric duality or not? So it's not clear if there's two different canonically driven dualities between this space. This space is obviously a little bit interesting in the even dimensional condition. So there's all of those dualities to look at. But there's actually, it seems like how much more can there be? I've connected everything, right? But there's actually one other that's a lot less talked about than these, but it's worth noting. And I'm trying to think, how am I going to draw it? I'm going to have to draw it on another sheet. So I'm going to start another sheet. So there's another set of dualities, and I like to put these together on top. I guess there's an alternative way of doing it. Since I did it this way last time, why don't I look at it again? Why don't I just separate them fully, right? Like that. Oops. They are the same space, though. That's why I'm tempted to kind of bind them together, because they're literally the same space. They're just referred to from as forms in one case, and as zero vectors in another case. Right. Now notice, so this is the sequence of p-forms, exterior power for p-forms. They all have this dimensionality, which we've kind of gone through, 1, 4, 6, 4, 1. But there's another immediately related space that has the same dimensionality as these guys. And that is how would I do it? Lambda 0 tensor product lambda 4. Lambda 1 tensor product lambda 4. Lambda 2 tensor product lambda 4. Lambda 3 tensor product lambda 4. Lambda 4 tensor product lambda 4. All of these have the same dimensionality 4, which is why I kind of made them horizontal. Because we remember when we studied the question of densities, tensor densities, we learned that whenever you take dx0 wedge, dx1 wedge, dx2 wedge, dx3, this was a one-dimensional object. And if we take the tensor product of a one-dimensional object with any other tensor, it does not change the dimensionality of the resulting object. Now the resulting object, this thing lives in a different tensor product space than just this thing. So you are moving from one tensor product space to another, but it has the same dimension because this guy here has only one basis vector, and therefore it can only have one component, which just sort of blends to the component. You know, if this is the component of this thing, and this is the component of this thing, this guy just comes out and merges and creates a new component here that has the same number of dimensions as this component had. We went through that before. So all of these tensor product spaces have the same dimensionality, and ultimately the price we paid for this was that we lost the principle of being a straight-up tensor, and we created tensor densities. And in fact, this can go on like this again. Tensor product, 4, tensor product, 4, etc., etc., etc. You could do this forever, and you never change the dimensionality of things. So there's this infinite sequence of densitized exterior power spaces. That's what these are called. These are called densitized exterior power spaces. And this is a singly densitized, doubly densitized, triply densitized. It goes on forever, and it does so for every one of these. So I'm not going to draw them all. I'm just going to draw these first ones, okay? Because that's really the ones that matter. And we know that if you are in the basis, if you are in the strict basis of any of these densitized spaces, that the transformation is as a tensor density. All right, so now we do the same thing over here. 0. Let me move that a little farther over. Lambda 0. I don't want green. Sorry. Lambda 0. Lambda 1, lambda 2, lambda 3, lambda 4, and then this guy goes obviously to lambda 0, and I'm going to put, since it's densitized, always means we're using the P form. That's what we're kind of dealing with, is the P form. Lambda 0, 4, lambda 0, 4, lambda 0, 4, lambda 0, lambda 4. Okay, so we have all of these guys. So the point of this is that now we can say, well, wait a minute. I know that I have mappings from, say, the third exterior power to the first exterior power of p vectors, right? I've got that mapping. But what's to say that I can't have a mapping from here to, oops. Why do I have zeros for all of these? That's silly, right? This should be 4, 3, 2, 1. So what's to say that I can't have a mapping from here to here, right? Or, for that matter, a mapping from here to here, right? What about that? So it's this mapping here seems like it might be kind of trivial because I just take this mapping, and I just append that to it, right? So we'll have to talk about this as our working with this stuff is what we'll do at the very either at the very end of this lecture, or I'll separate this for another lecture. Okay, so what we've done here is we've kind of discussed the spaces and the dimensions and pointed out the fact that spaces of the same dimension in the context of an inner product will always have a Hodge duality. It turns out these other dualities, Hodge duality and a metric duality. These green dualities, however, and some of the dualities we're going to talk about here, do not require an inner product. They do not require an inner product. So that's interesting. So we'll start with the Hodge duality for this lecture, and we'll probably cover the other one in a second lecture. All right, so now we're going to begin with Hodge duality. Now, I did discuss this in a previous lecture. I'm going to do it again now in the context, just in the context of our deeper understanding of these exterior powers. And we'll just roll it right into a series on all the different dualities. So the Hodge duality is an isomorphism between the pth exterior power and the n minus pth exterior power, right? So that is this guy right here, right? This connection here, these red lines, pth exterior power to n minus p. And it's true for the vector spaces as well, right? And pth exterior power 2, n minus p is 2, so it's the self-duality in this case. So that's the mapping, and it goes, because it's a duality, it goes both ways. You can think of it completely legitimately in both directions. It's not from p to n minus p or n minus p to p, it's both directions because it's an isomorphism. So we're seeking that mapping. Now, we already know one mapping that binds these two guys together, and that is the wedge product itself. The wedge product is a mapping that takes the pth exterior power, or an element of the pth exterior power, and an element of the n minus pth exterior power, and gives you an element of the nth exterior power. So remember, this guy here is essentially a pairing where, say, omega is a p form, and gamma is an n minus p form, and you end up with, through the wedge product, I guess I'll say wedge product is a map. If the wedge product, you end up with omega wedge gamma. And this mapping is, this kind of thing is called a pairing, by the way. Pairing means I take the Cartesian product of two things, of two spaces, and I take a map from that Cartesian product of two spaces to some third space, and that's a pairing between these two spaces. That mapping is a pairing, right? It's literally a pairing. So it's not too hard to understand. So this wedge product is a mapping that takes a pair and gives you an element of the nth exterior power. But what's important is that this thing is one-dimensional. This thing is one-dimensional, and that's really the thing that binds all of this together. Ultimately, every one of the dualities leans on the fact that the nth exterior power, where n is the dimensionality of the underlying vector space, right? That's important. The nth exterior power is one-dimensional. And that's really what drives all the dualities. Of course, for Hodge duality, you need to have that inner product, right? Right? You need the vector space itself has to have an inner product. But even if you had the inner product, you're not going to be able to create the Hodge duality without the fact that the nth exterior power is one-dimensional. And just to beat it up, right? You can imagine how an element of the pth exterior power would look like v. I'll just call them. Let's see, what do I want to call them? Omega. If omega is a one form, so omega 1 wedge omega 2 dot 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 wedge omega p, right? That's a p form. You wedge that with a gamma 1 dot 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 wedge gamma n minus p. You're going to end up with omega 1 wedge dot 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 omega p wedge gamma 1 dot 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 wedge gamma n minus p, and this thing is going to be an n form, right? That's how you can kind of break. You can always do this. You break it down into a simple one form wedge with a simple p form, and remember, everything's linear in this thing. So if I can show it for a simple one p form and a simple n minus p form, I know it's true for a general p form, which is a sum of things that look like this, and a sum of n minus p which look like that. It's just linear. This guy, this wedge, we know is linear, and that's really important. All of this stuff depends on being linear, and being linear means we can make our proofs for simple forms. Remember, a simple form is a form that can be written as one term of one forms. Arbitrary one forms, these don't have to be basis one forms, but imagine that right here I have a bunch of arbitrary one forms, and don't get confused. Remember, omega 1, that's the name of the one form, so it's going to be omega 1 alpha dx alpha, right? Because this superscript is a name of this thing, and I'm doing that so I can name p different ones, and here I need to name n minus p different one forms. And so these superscripts are not space-time superscripts. This is a space-time subscript. Remember, these are forms, so the components of forms are covariant, whereas the basis vectors of forms are contravariant, right? So these subscripts here, these little subscripts are part of the names of these vectors. I'll just beat this to death because when you read books, different books, they have different techniques for showing this. Sometimes they won't number it like that. What they'll do is they'll say omega wedge alpha dot 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 wedge beta, and then they'll say p terms, right? They'll have to write down that there's p of those guys, wedge, and then they'll say v wedge w dot 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 wedge z, and then they'll say n minus p terms, right? And then they'll say this whole thing has n terms, right? That's kind of crazy. So, but this form has the problem of being a little confusing because you've got indices that are not space-time indices. They're part of the names of these objects. Okay, anyway, we actually dealt with that problem before, so it's not the first time I've explained that. Okay, so where are we? Yes, one-dimensional. So I pointed out that this mapping here ends up in a one-dimensional vector space. Okay, so now the next step of important realization is that we are dealing with an inner product space. Remember, I told you that the Hodge dual depends on this inner product. So how does that depend on the inner product? Well, the inner product on the underlying vector space induces an inner product on the pth exterior power, right? That means this guy here is an inner product on the pth exterior power. So I can say the pth exterior power is an inner product space also. And that inner product is forced upon us by this guy. That doesn't mean you couldn't invent a different inner product on this space. But if you did, it'd be arbitrary. It'd be a second arbitrary inner product. This way, you've created an arbitrary inner product for V. Or when I say we've created an arbitrary inner product, I got to be a little careful. What I mean is, if an arbitrary inner product is selected for V, it will canonically force us to have an inner product on the pth exterior power. I don't want to say arbitrary too much about the inner product, because ultimately in general relativity, the laws of nature force us an inner product on V, right? So it's the laws of nature. It's not arbitrary. It's the laws of nature that are doing it. But right now we're speaking abstractly. Maybe I could say, you know, the laws of nature give us an inner product on V, and that forces an inner product on the exterior power. Although I'm speaking in mathematical terms here, so it's kind of silly to appeal to nature for my inner product. So why don't I stick, yeah, okay, so I'm going to stick with my original thing, which is we're the mathematicians here, we create our inner product on V. This guy here, that's us, right? So we've created this, but once we've created that, we're stuck with the fact that we get this, and therefore the pth exterior power is an inner product. And so, well, what does that mean? Well, it means exactly what we would expect it to mean. It means that this thing here, it's looking for a P form and a P form, right? An inner product is going to be a map from, it's going to be a self-pairing to the real numbers, right? And so I get two P forms and I get a real number out of it. So what real number is it? Well, if I put in a P form omega and a P form gamma into the P exterior power inner product, I am going to get a P form that I'm going to get well, I'll write it again. I'll get an element of the real numbers. So how would this look? Well, the P form, now we go back to this idea up here of using one forms to illustrate our process. So, so if the one form in question is omega 1 wedge ... omega p and gamma 1 wedge ... gamma p, that inner product is the determinant of the matrix of inner products on V of omega 1 omega I gamma j V star. Remember, so that's a good point. This is a good time to show this. Where's that inner product? This inner product here, right? The first thing it does is it creates a dual space with an inner product on the dual space, right? Right. So that's automatic, right? We've already kind of shown how that worked. So this determinant down here, since we're dealing with one forms, this inner product here is induced by this inner product from the vector space. So this vector space induces that inner product, and then you could argue that this inner product, this inner product is what induces that inner product. It's a little bit of a string of inducements, but they're all canonical, they're all forced upon us. So this is the expression for the induced inner product of the P forms. It's this determinant, right? And you can imagine why this determinant appears. These determinants show up a lot in this study, and that shouldn't be much of a surprise. In fact, I'm pretty sure we worked this out in a previous lecture. All right, so now we can finally put together all these ideas and get our sense of duality. Because what we've now shown is that we have two different ways of making a real number out of an element of delta p. The first way is we take this element of delta p, let's call it omega, and we run omega through the inner product on delta p, right? We run omega through the inner product on delta p, and we'll end up with a real number. The problem with this technique is that we actually need another member of delta p to put in that first slot, right? So if I take omega and I run it through this, I will get a real number. I choose a beta, I choose some other member of delta p, I put it in this first slot of the inner product, and then I take omega and I can put it in, I take beta and I put it in the second slot of the inner product, then I take omega and I put it in the first slot of the inner product, and I get R. Now, I said first and second and first, but these things are symmetrical. The inner product is symmetric, so it really doesn't matter. So if I'm given a B, I can take any other element of the inner product and I can create a real number that way. So that's one method. I have to create, in order to do this though, I need sort of a reference P form to slide into one of the slots on this inner product. And then any other member of the pth exterior power, I can generate a real number. So that's one way. We'll call that method 1. All right, so method 2 is I take an element of the exterior power, call it omega, and what I'm going to do is I'm going to take an element of the n minus pth exterior power, and maybe I'll call that alpha, and then I form omega wedge alpha. And that thing is going to be some constant x, which is a constant, and it's going to be a constant x times what I've called E, where E is our unit density. I got to be careful because I say unit density, but it's frequently called the unit volume, right? And that is the, remember, it's an element of the nth exterior power, which is one-dimensional. And that's why we can write this down, because this thing is one-dimensional, and x is therefore an element of the real numbers, right? So if I peel away x, it's unique, right? Because this thing is one-dimensional, and x is a real number. So I generate the real number by having some element of the n minus pth exterior power, and I wedge it with my omega, and it produces an element of this one-dimensional vector space, and the component is a real number. And I can claim that that's a real number associated with omega. The downfall here is I have to have an element of the n minus pth power to go here to make this process. So this second method of doing this is similar to the first method in the sense that I kind of have to pick out a special guy from some exterior power space, in this case the same, and in this case a different one, in order to create this process of generating a real number, right? These are two different methods to create a real number from omega, with the caveat that in both cases you still need another form, not necessarily from the same space, but you need to pick another form in order to execute the process. So what we do now is we say, what happens if we demand these two processes yield the same result? That means we want omega inner product with beta, using the induced pth exterior forms inner product, that has to equal x, this thing x, right? And when that is the case, right, what we're kind of saying is that omega wedge alpha equals omega inner product beta p times this unit density, right, times this unit density. And this expression ties alpha and beta together. And when this is true, we say that alpha is the Hodge dual of beta. And we can now write omega wedge Hodge dual of beta equals omega beta E, or the equivalent, omega wedge beta equals the Hodge dual of omega wedge B in the n minus pth inner product spaces process, inner product spaces, induced inner product, and the unit density. And these two are equivalent, and I put them both down because different books will define it one way or the other, and so I'm wanting to show you both ways. We kind of went in this direction. I think it's a little easier to go in that direction, only because we've been talking about this inner product, but this inner product is just as legit. You know, every pth exterior form has an induced inner product, including the n minus pth, so that's not a problem. So what are we kind of looking at here? Well, we're basically saying that if I take omega and I wedge it with the Hodge dual of beta, then if I take the inner product of omega with beta and slap it against the unit density, I'm going to get the same thing. And so clearly the Hodge dual of something exists in the complementary space, the n minus pth exterior power. Likewise, I can think of it this way. For every vector beta, there is a Hodge dual such that if I take omega, if every vector omega, there is a Hodge dual of omega, such that if I take the wedge product of omega with an element in the complementary space, I end up with the Hodge dual of omega, the inner product of that with beta in the complementary space, times the volume form. That's going to be equal, right? And so what I've done is I've set these things up to be, I've set these two methods up to be the same. And the reason this works is because there's only one real number here in method 2. And the reason there's only one real number in method 2 is because the top exterior power is one-dimensional. If it was anything else, I would have two real numbers here, and I can't really marry up these techniques. So this is the definition of the Hodge dual. It takes a little bit of thinking to work it out, but it's really, you know, just a little bit of practice, and you should be able to get here pretty smoothly. So, but ultimately, Hodge duality, which is this little star operation, right? It's an operation that takes a member of the pth exterior power and sends it directly to the n minus pth exterior power. Now it's funny, I usually write it both ways like this, but I mean, it's obvious, right? N minus p, I just call it q, and I can write it both ways. But the point is this is the mapping from p to n minus p, and you can prove a whole bunch of things about it. First of all, it's linear, right? That's an important point, which means the Hodge dual of a real number a times omega equals a times the Hodge dual of omega, right? And the Hodge dual of omega plus beta, where omega, remember, omega plus beta means that omega is a p form and beta is a p form, because this addition sign is a vector addition sign. So both guys on both sides have to be in the same vector product space. So the Hodge dual, and obviously the Hodge dual is a map from p to n minus p. So this thing here better be an element of the pth exterior power, right? But anyway, the point is it's the Hodge dual of omega plus the Hodge dual of beta, where now this addition sign is in the n minus p exterior power space, right? That's the vector addition of the n minus p exterior power. It's always good to keep track of where these plus signs belong and what they mean. These are different plus signs. You could literally put a p here. Well, maybe I should write it clear. You could actually do this. You could actually do omega plus with a little p, beta, equals, and in fact, you could put one here too, right? Because I'm doing the Hodge dual. In fact, I should put a p right there, right? Because I need to know what the domain is of this operator, right? Because there's another Hodge dual operator that takes, well, for example, there's a Hodge dual operator that takes 1, 2, 3, right? Then there's a Hodge dual that takes 2 to 2, right? Well, how do I know the difference between these two? Well, here I should put a little 1, and here I should put a little 2. And in fact, sometimes that's done. Usually, however, it's not. And the presumption is that if I have the Hodge dual of omega, I'm talking about the Hodge dual of whatever omega belongs to, whatever space omega belongs to. If that's an element of 3, then I just know that that's the Hodge dual that takes 3 to 1, right? But you could put it there, just like you could indicate the vector space on each addition, right? So I could put this star omega plus n minus p, Hodge beta, and here I should probably put, right under there, I should put an n minus p, and here I should put an n minus p, just so everybody knows, right? So you could go that far with this notation if you wanted to, and sometimes for illustrative purposes it's actually done that way. But it's linear is my point, okay? That's the big point you've got to take away. It's linear. And the reason that's important is because if we can find the Hodge duals of the basis vectors of a space, then it's very easy to find the Hodge dual of any vector of the space, because linearity will just pull the components out. You'll swap the vectors for the basis vectors for their Hodge duals, and then make sure the signs are all lying in the right place, and you'll be fine. Okay, anyway, so now let's just spend a moment and have a look at how these definitions work. Let me sort of shake down this definition here, and I'm going to copy it and put it over here. Okay, so let's have a quick look at this definition. Let's do it for a really easy case. Let's look for the Hodge dual. Let's go to this weird exterior power, the 0th exterior power. The basis vector, the 0th exterior power, is the number 1, right? The number 1. And I'll make it a little bold. The boldface won't last long, I'm sure, but to indicate 1 as the basis vector of this space is fine. We'll just go with that notation. I'll probably end up just drawing the number 1 like that. Let's just say if I draw the number 1 with some effort to ornament it, then we're talking about the basis vector of the 0th exterior power. So I want to find, look, this is the 0th exterior power is an exterior power space. It's an exterior power space that happens to be the set of functions. So let's dispatch with it so we understand exactly how it works. But being an exterior power space, it does have a Hodge dual. Heck, I might even go ahead and put a little 0 there just to entertain myself with exotic notation. So I want to find the Hodge dual of 1. And I know that in that case, the Hodge dual for the 0th exterior power takes an element of the 0th exterior power and is going to return an element of the n minus 0 exterior power, which is the top form n, right? So sure, this is the dimensions all check here, right? This is one-dimensional, this is one-dimensional, so that shouldn't be a problem. There I have my Hodge dual with my little extra 0 in there. How would I do that? Well, let's see. I would write an arbitrary vector omega, Hodge dual, or wedge product with the Hodge dual of 1 should equal the inner product of omega with 1 held in the pth exterior power space times dx0 wedge ... dxn. Now let me make one important point here is, remember, this guy here I'm calling E. And I've said that I've chosen that this particular arrangement, x0 through xn, that's going to be our positive orientation. I'll call it positive orientation. We could also call it, it's going to be our right-handed orientation, our right-handed system. That's an arbitrary choice, by the way. You know, if I'm in Cartesian coordinates, it's x, y, z, you know, and I've chosen that, okay, x rotating into y should revolve around z. Fair enough, right? And I've also decided, for example, that, you know, if I was in the spherical system, I say r, and then I have to choose, r sometimes usually goes first, right? The radial direction almost intuitively goes first. And then I think most people like to go with the, what is that? The azimuthal direction? No, not the azimuthal direction. The, which is the one off of the z-axis? Which one is this? I think azimuth is always phi, and phi usually goes third, right? Because z usually goes third in x, y, and z, so rotations around z ends up going third in spherical coordinates. So that's azimuthal. I'm forgetting the name for the guy in the middle here. It'll come back to me. But the point is we choose that in this system, dr wedge d theta wedge d phi, we choose that that's going to be the positive orientation of the system. So we've made that arbitrary choice. I'll talk a little bit more about that in a later lecture, because orientation is a big deal here. Ultimately, orientation matters quite a bit. But it is a very simple choice. It's one of two things. It's positive or negative, and we've just chosen that this is our positive orientation. Okay, so continuing on, this is sort of our statement of this, right? There's our definition right there. The definition of the Hodge dual of 1 means that this thing here is true. So what's the value of this guy? Well, first of all, how do we make sense of this? Well, this only makes sense if omega is an element of the zeroth exterior power, right? So what this is saying is that an element of the zeroth exterior power wedged with an element of the Hodge dual, well, the Hodge dual, this guy has got to be an element of the nth exterior power. But that's exactly what it is. Whoops, let me put my little zero there, because we know that the Hodge dual is a map into the nth exterior power. So omega has to be chosen from the zeroth exterior power, which means that this whole term, right, this whole term here is omega inner product with the unit, it's a function inner product with the unit, which is going to be the function itself. It's going to equal omega. So that thing equals omega. So omega wedged with the Hodge dual of the unit of the zeroth exterior power is got to equal omega times E. Well, this ends up being omega, which is now a number because of its membership in the zeroth exterior power. Omega times the Hodge dual of 1 is omega times E, so the Hodge dual of 1 equals E. The Hodge dual of the unit equals E. Now you'll notice this analysis of the Hodge dual of the unit of the basis vector of the zeroth exterior power always equals E, right? This logic works for any dimensionality, right? For any dimensionality, as long as the unit volume form is here, this guy is always going to equal omega, which is a number, and so this expression will be true in every single circumstance. What's not always true, and I'm saying this a little bit of foreshadowing, it's not always true that the Hodge dual of the Hodge dual is going to equal E, or is going to equal, whoops, what am I doing here? That's never true. The Hodge dual of the Hodge dual will not necessarily always equal 1. That's not always true. By the way, this should be using our little fancy extra notation. This is the Hodge dual of n times the Hodge dual of 0, right? It's not really the same Hodge dual, right? It's two different Hodge duals. But we understand that, right? Everybody understands that you're taking the Hodge dual of the appropriate mapping, right? So you usually see it written this way. You almost never see it written that way. But hey, this is our first time going through it, so I want to emphasize this fact. Anyway, this is not always true. So we'll get into an example where it's not true later. Well, we're almost there. In fact, right now we have demonstrated this example or this definition with this exterior power space, and we've come up with something that's always true. The Hodge dual of the basis vector for the 0th exterior power is E, which right away tells us, because of linearity, the Hodge dual, the 0th exterior power of any omega is going to equal omega E. And that's because it goes like this. The Hodge dual, the 0th Hodge dual of omega equals the 0th Hodge dual of omega times the basis vector 1, which equals omega times the 0th Hodge dual of 1, which equals omega E, right? Always true. Okay, so what's our next example? Well, let's take the other one-dimensional space out there in our pantheon, which is the nth, the top form, right? That is the every element of that space looks like omega E. Or again, E is our unit density or unit volume. I'll talk about this question of whether we call it the unit density or the unit volume. It has to do with how you think about integration of a form. I should make that out. If W is a P form, you can integrate that P form, but you integrate it over some volume or some type of volume. And you can think of the volume form going down here, and then this is the volume element being down in the integral, and then this is ultimately some kind of form. And how you think about this is how you think about whether or not it's a density or a volume. The point is to understand what's going on and not worrying about this too much. It's typically, this is called the unit volume more than the unit density. So I'm going to go with unit volume here. So let's consider this, right? So we do sort of the same thing. We are now going to say, all right, I'm going to take omega wedge. I guess I'll put my little n in there. I'll just sort of keep that going on for now. This equals omega E, the inner product in the nth exterior power with the unit volume here, right? So how does that work? Well, in order for this to make sense, we have to pick an omega that's an element of the top exterior power. And once we do that, we end up with, well, we can choose one. Let's choose, in this case, let's choose E. Let's choose E. I want this to kind of come out simple. So I'm going to put in omega equals E. Right, so remember, this guy here is going to be a real number. And then over here I get E wedge the Hodge dual of E. Well, E wedge times, well, so what are we dealing with now? Well, what is this guy? Right? Well, this guy is going to be, let's take the basis vectors to be E1 wedge dot 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 wedge En, where E mu is the basis. That's the basis of V. of the underlying vector space V. So it's that with, well, with itself, E1 wedge dot 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 wedge En in the nth exterior power space. And we know what this is. We did this in a previous lecture. This is simply the determinant of the matrix that looks like EI, EJ in V star, right? So that's this determinant. And that's easy to figure out, right? Because we're going to be dealing with, so now this all depends very much on this inner product, right? But it's ultimately easy to figure out, especially if we're dealing with this pseudo-Riemannian inner product space, because every one of these terms here is going to be plus or minus 1, right? For example, you know, in our classic Lorentzian space, E0, E0 in V dual was equal to minus 1, right? So ultimately, this determinant is always going to equal minus 1 times n minus s, where s is the signature, or, well, it's the number of positive eigenvalues in the metric, right? So if the metric ultimately ends up with the one we use the most, which is minus 1, 1, 1, 1, then s equals 3, because there's 3 positive eigenvalues. The alternative definition is plus 1, minus 1, minus 1, minus 1, in which case s equals 1. Notice, however, in both circumstances here, s is odd. So this determinant is equal to this sign here, right? So that's an important, that is what this guy is on this side. It is going to equal minus 1 to the n minus s, where s is the signature of our inner product, which is not all. Now, if we're using normal Euclidean space, of course, the signature is going to be 4, if it's 4-dimensional Euclidean space. If our dimensionality of our universe was 3, which is sort of the elementary physics case, and we're using Euclidean space, which is also the elementary case, s is going to equal n, which is going to equal 3, and n minus s is going to equal 0, and the answer, and then this whole thing is going to equal 1 for that elementary case. For the case of a Lorentzian inner product, you're going to have n equals 4, and s is going to be, using my favorite one here, 3. You get 4 minus 3 equals 1, so you get minus 1 to the 1, so you get minus 1, right? Get minus 1. So this is where the actual nature of your underlying vector space really hits home, right? It hits home when you start to calculate the Hodge dual of the unit volume. You could get a 1 or you could get a minus 1 on this right-hand side. Okay, but moving on, this only makes sense, of course, if the Hodge dual is a 0 form, right? But of course the Hodge dual is a 0 form because it's a map from P to n minus P, right? It's a map from P to n minus P. So it's a map from n to n minus n, which is 0, right? So this makes perfect sense. And so the last step here is to simply write down, my black, that the Hodge dual of E, dropping the n this time, is minus 1 to the n minus s of 1, right? So, and that, I guess I should write it out this way, is this guy here becomes Hodge dual n of E times E, right? Because remember, this just becomes a number that's living in the 0th exterior power, so this wedge just becomes regular multiplication in that case, right? So this is a number, an E, And we know what this number is. It's minus 1 n minus s of e. And now we just equate the two components to get this expression here. So now you see that the Hodge dual of the volume form has this dependence on the signature of the metric, right? Very interesting. And how did that arrive? That arrived from this inner product here, right? This inner product here. And ultimately, that's because you can trace this to, if you diagonalize this thing, if you choose your basis to be orthonormal, right, you end up with just multiplying straight down the diagonal for this determinant, and that's what ends up with this guy right here. Okay, you can work that out a little bit yourself. It's not that important. I mean, we've already done this definition, and that's really what matters. So now we've solved two cases. We've done the case, we found the Hodge dual of everything in the 0 exterior power and the nth exterior power. We've found those Hodge duals. The reason is because if I have something in the nth exterior power, omega, the Hodge dual of omega is the Hodge dual of omega times e, which is omega, where omega is a real number, right? The component, so I guess here I need the boldface form. Here I have so it's the component times the Hodge dual n of e, which is going to equal minus 1 to the n minus s omega, n minus s omega times 1, right? Times 1 times the 1 basis vector. Okay? So those two cases are done. Maybe I need to be a little bit more. So think of it this way regarding this minus 1 to the n minus s term, right? Think of it this way: e I e j in in the inner product space on V. That's going to equal delta I j plus or minus delta ij for an orthonormal basis. That's what an orthonormal basis means in a pseudo-Riemannian metric. So if we have a pseudo-R metric, this is an expression of orthonormality, right? Two basis vectors run through the inner product of the dual space is going to either be 1 or minus 1, and the two indices have to be the same. So when I take the determinant, this would be a j, right, of this expression, ei, ej, v star, I'm asking for the determinant of a metric where I have I guess I'll start with 1, e1, e1, and then all of these off-diagonal elements are going to give me 0 because of this delta function. So I only have e1, e1, e2, e2, to en, en, like that. So the determinant of that is just the product of the guys along the diagonal, right? So how many diagonal elements are there? Well, there are n diagonal elements. So now, of those n diagonal elements, there are going to be S of them are positive. S of these are greater than 0, right? So how many factors of -1 are there? Well, there are n minus s factors of -1. So the value of this determinant is -1 to the n minus s power. That's what drives the sign, or the result of this determinant for this orthogonal pseudo-Riemannian coordinate system. So, so that's how this determinant ends up getting this value. You're choosing an orthonormal pseudo-Riemannian. Well, let's put it this way. You have a pseudo-Riemannian metric, and you've chosen an orthonormal basis in that metric, and therefore you end up with your determinant. And that's not a lot to ask for. So that is how ultimately this expression here lands us, lands us here, which also lands us here, right? And it has to, right? The nature of the metric, there's only a few different kinds of possible metrics out there, by the way. And they're basically measured by how many negative signs show up in this determinant. Now, the one that's used in special and general relativity always has either 3 positive and 1 negative, or 1 negative and 3 positive, right? There's 2 different conventions out there. One's called the East Coast and one's called the West Coast convention. I forget which is which right now. But they end up, it turns out, yielding the same results for these determinants. All right, so now we have to do this for a general inner product space. We have to do this for a general inner product space, lambda p. And it's all the same logic, but it's just, we have to play around with our notation a little better. First of all, we're going to stick with this, right? This is our thing. We're going to have this orthonormal basis, right? That makes it easy to understand how this determinant works out, right? So we're sticking with this orthonormal basis for a pseudo-Riemannian metric, and that pseudo-Riemannian metric is going to have a signature S. I'm kind of doing this in full generality. If you go to a lot of books, you're going to end up seeing them do this in either 3 dimensions for the engineers out there. Usually what it comes down to this. If you're an engineer and you run across the concept of forms, they stick to 3 dimensions and Euclidean metrics, because they figure engineers can't think beyond 3 dimensions, and God forbid the Pythagorean rule shouldn't be in effect. That would just like blow their minds, right? If you're a physicist and you're past your sophomore year, you think in 4 dimensions with a pseudo-Riemannian metric or a Lorentzian metric that has a signature -1, +1, +1, +1, right? So then you guys are sort of stretching your minds a little bit, or I should say us guys are stretching our minds a little bit, trying to wrap our heads around the fact that space-time is 4-dimensional, time is just another entwined aspect of it, and distances are not Pythagorean. They are Lorentzian. Oh my God. So they'll develop this whole theory for either this case or this case. And then what they usually do is they reteach electromagnetism to engineers using this method, just to show engineers, man, if you really extend your thinking into this notion of forms, you can really get a great perspective on how electromagnetism works, right? And yeah, I guess it's true. But you can also study electromagnetism in n = 4 Lorentzian, and then you really got it down. Of course, this isn't the most practical way to do the standard calculations an electrical engineer might want to do. Or maybe it is. I mean, you can do it in any one of these ways. But the point is this one, so I'm going to teach electromagnetism in both ways, just to compare the two later. But we got to get through Hodge duality before we can do that. But usually they just go through these 2 cases. So this is n = 3, s = 0, or I guess s = 3. And this is n = 4, s = 3. But I'm teaching it with n and s, right? I'm just kind of doing it in full generality. So now I'm going to talk about p-forms. The only possible p-form in this circumstance that's not 0 or 3 is 1 and 2. And in this circumstance, it's 1, 2, and 3. But of course, for p, it's greater than or equal to 1, less than n, right? Or I guess, how about greater than 0, less than n? So nailing it down into this circumstance is a little bit tougher. But we are always going to lean on this sort of orthonormal set of vectors in our based orthonormal with respect to some pseudo-Riemannian metric of signature S, arbitrary signature. Okay, so with that in mind, let's begin. So we're going to start with a p-form. So omega is an element of the pth exterior power. And we're going to just consider a simple p-form. So I'm going to consider something that is a component times, say, E I1 wedge E I2 dot 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 wedge E I P. So there's P unit vectors wedged together in some order. And this is a simple P form. This is one term, right? Notice I'm not summing over these i's, right? I'm not summing over these i's. I should, it's just a simple constant times this thing. And in fact, why don't I just get rid of the A and let's look at just this guy, this unit P form. If I can prove all my stuff for this guy, by linearity I can prove it for your general P form. So we work with just this guy. And we're going to do it for this particular series of indices, right? This particular sequence, it's ordered too. So it's I1 dot 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 to IP. And I'm going to call that ordered, I guess if it's ordered I should put it in parentheses, otherwise it looks like some set. And I'm going to call that a multi-index I. I'm going to leave that a multi-index I like that. So that represents, this capital I represents this sequence of indices. Okay. So once I have a sequence of indices 1 through P, there is a corresponding set of indices that are not on the list. And I'll call those J1 through Jn minus P. There's n minus P of those guys, and they're not in this list. So so if I combine this list with this list, and I'm going to call that sequence H, I will get the list I, comma, H, and that is going to be I1 to IP, J1 to Jn minus P, and of course there's going to be n. That's going to be a list n long, and that list will be I, comma, H, right? That just means concatenation of the two lists. And these lists do not have to be strict, right? We're not forcing I1 less than I2 less than IP or anything like that, right? Certainly, even if we did, this list would not be increasing, because if I chose 1, 5, 6, 7 to be the first list, then I would have to ultimately have 2, 3, and 4 in the second list, right? And clearly that's not increasing. So we don't enforce increasingness, strictness. We don't enforce the strict rule on any of this. So we can build the basis of, so because we're not enforcing the strict ordering, we can build the basis of the top form n by wedging together constructions from P and n minus P, where n minus P is constructed by J1 wedge J2 wedge Jn minus P, like that. So this is an element of the n minus P, and we just create these same orthonormal vectors. Remember, these guys here come from V, right? So these are the same E's that we use for the pth exterior power. We use in the n minus pth exterior power, and we just take J of those, and they're complementary. We know that Ji will never equal Ik, right? There's no I's and K's where these guys are equal. They're complementary sets. And because of that, I can create an element of the nth exterior power by concatenating those two together. I can go EI1 wedge EIP wedge EJ1 wedge EJn minus P, and this guy here is an element of the nth exterior power. But what element is it? Well, it goes like this. It goes EI1 wedge EIP wedge EJ1 wedge EJn minus P is going to equal the Levi-Civita symbol on I comma h times the volume form. Well, I don't want to put that times the unit volume form. That unit volume form appears again. And again, the unit volume form establishes our positive orientation of this thing. So this guy here, that's just simply a true statement. And the fact that we haven't forced any strictness on these guys, and certainly not on this, that is all worked out by throwing this down. This Levi-Civita symbol will track the whole thing. And the I comma h just means concatenating all of these things together. And because none of the members of I are the same as the members of h, you'll never have a duplicate in this sequence, and therefore this will either be plus or minus 1. It'll never be 0. So this is just an expression that you take an element of p and an element of n minus p, wedge them together, and you get an element of the top form. So now, in order to keep this lecture from going on any longer than it must, I'm going to write down the ultimate result of this calculation, which goes like this. The Hodge dual, right, of EI1 wedge EIP. That's essentially saying the Hodge dual of a basis vector of the pth exterior power, right? Because I could choose I1 to IP to be strict. And if I do, then it's a strict basis vector of the pth exterior power. But a Hodge dual of, strict or not, the Hodge dual of any construction of that form is going to equal the following thing. It's going to equal this Levi-Civita symbol, right, which is very well defined because it's the I is, once you've chosen these I's, you choose what's on the left-hand side, right? So we choose the sequence of I's and we put it right there, right? We put it right there. And then we multiply. And now we're going to multiply by the inner products of EI1, and this inner product, of course, happens in the dual space, all the way through EIP in the dual space, like that. And then the result, then over here, we have EJ1 wedge EJN minus P. And that's the formula. That formula is the critical formula for the Hodge dual of an arbitrary basis vector or basis-like vector of an element of the pth exterior power. And you can see how the logic works here. You choose these i's through p's, that choice lands here, and that choice lands here. Now notice, this is going to take up and account for all of the vagaries of, well, not the vagaries, all of the specific signature of the inner product of the pseudo-Riemannian metric, because I1, these guys are always going to equal delta ij, delta ik, delta, God damn it, delta I, say, k, ik, that's going to be plus or minus these delta numbers. Well, no, I don't even need to write that. These guys are always going to be plus or minus 1 because of our orthonormal basis choice. How many are plus 1 or how many are minus 1 depends on the signature, right? Most of these, in our case, for the old n equals 4, s equals 3 case, most of them are plus 1, except for usually 0, 0, right? But this product is not like the full determinant or anything. It's just the product of the inner, it's the product of the inner product of just the guys on the left-hand side, which is not all of them, right? And so sometimes minus 1s will appear in here, and sometimes they won't. Sometimes there'll be more than one. Sometimes they could all be negative. The number of them will depend on P, right? There could be an even number of products here. It all depends on what you're looking for. There's no summation over here either, by the way. because there's only one possible sequence of j's, right? It's everything that's left over after you've picked I1 through IP. You have your set of j's is completely fixed. The ordering of the j's is arbitrary, right? This statement, it doesn't matter how you order the j's here, because however you order the j's here, it's only going to differ by a sign flip, and that sign flip is accounted for in this Levi-Civita symbol. So this is our formula for the Hodge dual of basis vectors in any exterior power space. And once you know that, I can take any element of this exterior power space, expand it in terms of basis vectors, and through linearity replace each basis vector with its Hodge dual, and I've got the Hodge dual of any element of the exterior power space. So our last thing here is we will actually now do some examples in this space here and in this space here, just to close out how those formulas work. Oh, wait a minute. This lecture has gone on way too long. I can't in good conscience continue. It's already like an hour and 40 minutes. That's crazy. I'll do the examples in a separate lecture, guys. See you next time.